Now I wanted to revisit an algorithm that we did last term, the depth first search algorithm. And here's a very basic description of the algorithm. You start at an initial node. Okay, you start at a starting node, so this one looks like it's starting at A. Okay. And what you do is you put the initial node onto a stack. Then you remove the next element from the stack and call it the current node. And then if the current node was seen, okay, by putting a circle around it or marking it in some way, then you skip it and you go to step 6. Okay, this goes step 6 and it goes to step 2. Remove the next element from the stack and call it the current. Otherwise, mark the current node as seen. Get all the neighbours of the current node and add them to the stack. Okay, so the neighbours of the current node A are B, C, and D. So if we added those to a stack, so imagine if we had a stack here. Okay, we would add them in order, so we would process them alphabetically. We would put D, C, B on the stack. Okay, so A has already been visited, so all the neighbours of A are B, C, and D. We would go to the top of the stack, take off that B. Okay, that's the current node. Pop it off. B. That's the current node we're processing. Look at the neighbours of B. Okay. Get all the neighbours of the current node and put them onto the stack. Okay, the neighbours of B that haven't been already seen are E. That's about it. So stick E on top of the stack. So this will be the next step. B's already been taken off. So we've got C, D. E's taken off. We put E on top of the stack. Okay, so E is the next node that gets visited, gets popped off the stack. Look at the neighbours of E, put them on the stack. Okay, the stack's still got D and C on it. And the neighbours of E are B, well that's already been processed, forget about that one. D and G. And in alphabetical order we should put G down first because we want to process in alphabetical order, and D on the top. Okay, so now we look, we've processed E. Okay, if you remember this from first term, now we go to D. D is the top of the stack, that's the next one we look at. Okay, and on we go. Okay, so this is doing this by iteration. Okay, so this is iteratively popping off the stack until the stack is empty. So it keeps on doing it until the stack becomes empty, and that's what stops it from iterating. So remember this algorithm. Who remembers that one? Hopefully you remember that. Yeah? Good, because we're going to make a recursive version of depth first search. We're going to go in an alphabetical order. In depth first search, you've got to place them on the stack so that they are processed in alphabetical order. So when we were back here at A, we had 3 choices. We could have gone to C, to D, and to B, but because we want to process in alphabetical order, we put them in the stack in the order B, C, D, reverse alphabetic order, so that we would process, we would end up visiting them in alphabetic order. Recursive depth first search. Okay, so this is an algorithm I got from Wikipedia. To run a recursive depth first search, that previous version we just went through was iterative, you need a couple of inputs. You need to have obviously a graph of nodes and edges and a starting vertex in the graph, or a starting node to begin with. So this is the recursive version. Okay, so it goes in here, it sets up an algorithm, if you like. Procedure is another word for a block or an algorithm. You label V as discovered, so you mark it as processed, whatever. And for all edges going from V to W, in edges, this means adjacent edges, neighbouring edges to the edge V, what do you do? Well, if the vertex W, which is the other end of the edge, hasn't been discovered or processed, then you recursively call depth first search with the end vertex. Okay, and that's going to go back in here. It's going to label W now. It's gone in and calling itself with W. W is labelled as being discovered or processed, and then it's going to look at the neighbours again of W, and it's going to pick one of those adjacent neighbours and recursively call from that point onwards. Anyone see how this is working, or getting an idea of how this is recursively processing a depth first search. So it's just going through as we had before. It's just picking one of the neighbours. So if you had a graph that went something like this, okay, so just say we had a graph that went something like this, and it had A, B, C, D, E, and F. Okay. The very first time we would call this would be DFS, my graph, and if I started at A, it would start at node A. Okay, so that's a starting node. It would mark that as visited or as discovered. Okay, that's the very first recursive call. Then inside there, it would look at the edges coming out of this node A. The other end of the edge, well, it could either pick B or C. For argument's sake, let's just say it picks to go to B. Doesn't matter where it goes, it's going to pick one of the neighbours. So it's going to mark that as visited. Okay, because the other end's not visited. Then it's going to be at B. So recursively at B, it's going to look at the neighbours that haven't already been visited. Well, A's been visited, but D and F haven't been visited. So it's going to pick one of those. Doesn't matter which one. Maybe D, this one, doesn't matter. So it's going to then recursively call itself again with D. Okay. And that's visited. Okay. And then what's it going to do? Well, it looks at the neighbours of D, any that haven't been visited there. It would pick either one of those, I don't know, C or E, doesn't matter. It might actually pick C, it could go back to here. Could go back to there, that one hasn't been visited. And it would call itself D, F, S, G, C. Okay. So now we're in the recursive call for C. Now what can we do here? This is going to reach a base case because C, all of C's neighbours have already been visited. So there's no other recursion that can happen from C. So it's going to maybe pop back. Is it going to pop back? That might be the end, actually. Oh, no, because it does it for all the edges. Okay. So B had another edge back up here. We've done D. D had another edge, actually. D had another edge. E, we didn't process that one, so let's process that one. This is at the same level. This is as the C, DFS graph E. Okay, from E, what can it do? It can recursively go to, the only place it can go to is F. Okay, so it's going to do another recursive call, DFS graph for F. And what can it do from F? F. All of F's neighbours have already been processed. It can't go into any more neighbours. It can't recursively call again. It's reached a base case. And it will pop out. It will pop back out to where we were processing B up here, because D's already been done. All the neighbours of D have been done. B, all the neighbours of B weren't explored, but now we can't keep on exploring them because they've all been visited. See how that empty node here, that yellow one, is indicating there's still a neighbour unprocessed, but that's already been visited, so we can't go there. And then it pops back to A, back to original call, to try and process all the neighbours of A again. We did B on the first pass through, but C is another neighbour, but it can no longer process C because C has already been marked as being visited. So that would be the recursive depth first search algorithm running on this particular graph. Okay, and it went there, and it went there, and it went there to C, then from D it went to E, then from E it went to F. Okay. Alright, how's that? During your It's more confusing than the normal DFS. So whoever's confused needs to call me during their study periods this week, and we'll go through it again. It's pretty tricky. Okay. I'm going to push on because I wanted to talk about another algorithm, best first search. And I want you to actually think about best first search. Best first search, this is the iterative version. It's so similar to depth first search. But the only difference, if you remember, is you use some rule. Well, before we were using depth first search, we were using alphabetic order. But there might be another reason why you might decide to put things on the stack in a particular order. You try to put the bestest on the top. How do you determine the bestest? Well, it depends on the scenario. What is the bestest next neighbouring node to visit? That's depending completely on the problem. I don't know. But it's really similar to depth first search. And of course, you can also implement best first search recursively as well. Okay? The same algorithm as before, but here, where you're deciding to choose the adjacent nodes, you might have a way of picking the bestest adjacent node that you possibly can that hasn't already been discovered or processed. Okay? So you would pick, sorry for that, I don't think that's a word actually, the bestest. When you've already got best in the title, where can you go? You can only go to the bestest. So you might change this to process the neighbours in the order of what you consider to be the best neighbour first. Okay, according to some rule or heuristic is the right word, rule of thumb, some rule or some intuition you have as to the best way to proceed from that particular node to the next neighbour. Okay, that's what best first search, why it's called best first search. Some reasoning, some know-how you have, some rule of thumb that you have to determine who is the best neighbour or the best way to go from that starting position.